Up until now, we've been talking about using a two-way ANOVA for an experiment. So either a full factorial design where everything's randomly assigned, or a randomized block design. But two-way ANOVA can also be used in observational studies. So let's use some data from 392 cars to look at how acceleration, that's the time it takes the car to go from 0 to 60 in seconds, is related to the weight of the car and horsepower. So these can be weight and horsepower can certainly be treated as quantitative, but in this example we're going to treat them both as categorical. So remember, anytime you want to do ANOVA, that's going to be for categorical predictors. So we've got our variables defined as weight, which is whether or not the car weighs over 2,800 kilograms, and horsepower is just high or low. So this is a common example to talk about confounding, because we might be interested in the relationship between the weight of the car and the acceleration. And we can see that the cars that are heavy tend to actually have faster acceleration, right? They have shorter acceleration times. So that doesn't really seem to make sense until you take into account horsepower. So horsepower is related to the weight of the car. So low horsepower is represented here by blue dots, and you can see that low horsepower cars tend to be light, and the high horsepower is represented by red dots, and you can see that the high horsepower cars tend to be heavy. And there's certainly some crossover in those two groups, but we can see the tendency. So heavier cars tend to have higher horsepower. We can also see that higher horsepower is associated with faster acceleration times because the red dots tend to be towards the bottom of the graph and the blue dots tend to be towards the top where the longer acceleration times. This graph in the notes is helpful if we want to look at confounding, if we want to see how all three of the variables are connected to each other. But if we just want to look at the association between the explanatory variables, there's an even simpler graph we can make. So I'm just going to go to Graph Builder, and I'm going to put the weight of the car on the x-axis and the horsepower on the y-axis. And I can see the association by the fact that these groups are not balanced. Right, I can see that there tends to be cars in the high horsepower heavy category or the low horsepower light category, right? There's a tendency for the variables to go together. They're not independent of each other. So when we design an experiment, we usually design it so that the explanatory variables will be perfectly independent of each other. So like in a balanced full factorial design, they're going to be independent. But in an observational study, there's often an association between the explanatory variables. And when there's an association between the explanatory variables, some of the math doesn't come out as nice as it has been up until this point. So specifically, the effect test and jump are going to show what's called adjusted sums of squares. So one thing that you'll notice about the adjusted sums of squares is that when you add them up, so I'm going to add the adjusted sums of squares for weight and horsepower. That's 758 and 597. I'm not going to keep all those decimal places. But you notice that that doesn't add up to the sum of squares for the model, which is confusing because this is what is explained by weight and horsepower. But when you add it up for weight and horsepower, it doesn't add up to the sum of squares for the model. So what's going on there? So it helps to know that this is just looking at the unique contribution of each explanatory variable. So I think it kind of helps to draw a picture. So we can think about the variability being explained by weight as this square. And this square is the variability being explained by horsepower. So notice there's some overlap here, and that's because there's an association between the two variables. So for weight, the sum of squares adjusted is 67.14. So this is the amount that's explained only by weight. And then for horsepower, we have 691.46. That's the part that's explained only by horsepower. But there's also this part here in the middle, and that's called the covariation. So if we look at the difference between the amounts explained by the model, 890.32, minus the sum of the adjusted sums of squares, which is 758.60, we get 131.72, and that's the covariation in the middle. So basically you have some of the same variability being explained by each of the variables. So how does that work? Basically, if you know the weight of the car, you're getting some information about the horsepower too, because you know that heavy cars tend to have higher horsepower. Same sort of thing about horsepower. If you know the horsepower of the car, you're sort of indirectly getting some information about the weight, because you know, for example, that low horsepower cars tend to be light. So there's some variability that's sort of being explained by both. So you can think of that covariation as like it could be explained by either of those explanatory variables. So if you were to fit a one-way ANOVA, if you were to do a model with only weight, that model would have the unique part for weight, 67.14, but it would also have the covariation, 131.72. So the total variability explained by that model would be 198.86. Same kind of thing if you were to fit a one-way ANOVA with only horsepower, the model with only horsepower, then you would get the 691.46, the part that's uniquely explained by horsepower, but you would also get the covariation, 131.72, and so total it would be 823.18. So it's kind of like either of those models could explain that covariation piece in the middle. It also sort of changes the way we interpret our p-value. So let's say we want to interpret the p-value for weight. That was 0.0005. So a very small p-value. So this tells us that we have strong evidence of an association between weight, that's the variable we're talking about right now, association between weight and acceleration. But we do have to add this tag because of the fact that we have a confounding variable. So there's a significant association between weight and association after adjusting for horsepower. And this is actually related to what we did way back in week 1 or 2. So you may want to go back and look at that, this idea of adjusting for another variable. So that's what it's doing when it calculates those sums of squares. So the math behind this is actually pretty gross. I'm not going to have you do these yourself, but I did just want to give you an idea of what JUMP is doing behind the scenes, that it does have to change its calculations when you have an observational study. So again, just to recap what's going on here, we've got shared variation, and that shared variation occurs in observational studies. That's what makes this different from all the other examples that we've seen in the notes. And the specific reason is when the explanatory variables are associated. So in this case, there's an association between the two explanatory variables. That's what causes this overlap or this covariation, and that's why we can't just neatly sum up our sums of squares and get the model sums of squares like we did before. This has some other small effects on the calculations too. So for example, when you do the effects in JUMP, the intercept is not going to be the overall mean. There's some other little things that change, but I'm not going to go into all the details, and I think it's best that we just let JUMP do the calculations. But I did want to point this out so you wouldn't get confused if you saw an observational study.